Good morning, everybody. Right, let's see. Thank you, Ernesto, Jason, Matthew, Corey, Fox, Marco, Dale. Thank you. Thank you, everybody. All right. So, in continuation of our discussion in complex analysis, last time I introduced um, trig functions. Now, today I am going to continue on trig functions and some of the major identities that we have in trigs, which is quite similar to what we had in pre-calculus or calculus, all right? So, starting with definition of trig functions, let me get to my whiteboard. Well, trig functions are not really something new. We talked about um, exponential function earlier, and this is sort of Euler's identity, and we are going to use e to the ix to define sine x and cosine x. All right. So this is what inspired us. You're looking just at Euler's identity. If you replace x by negative x, cosine of negative x is the same as cosine x. Sine of negative x is negative sine x. All right. So if you add them, you will get cosine x, which is right there. And if you subtract them, you will get this one. As I mentioned last time, we are going to follow exactly these two identities. Also here, although here x is a real number, but we will follow it by a complex number. So we will define cosine z and sine z, all right, exactly the same way, just replacing x by z. All right. Last time we sort of verified a bunch of trig identities. For example, what happens if we replace z by negative z here? Well, it is the same definition, by the way. Yeah, we do expect to get this. Cosine of negative z is the same as cosine z. And for sine, we do the same thing. This is just a verification by using exactly the definition of sine and cosine. Here is another one that I mentioned last time, and please note that if in your test I am asking you to verify a certain equation by using the definition of sine and cosine, this is what you will do, all right? For example, cosine of pi plus z. All right, you go ahead and replace in definition of cosine, you replace here z by pi plus z. This is you get. But on the other hand, we know that e to the I pi is -1, right? So you replace those negatives right there, and you will get this identity, okay? So that is what usually we do in mathematics. We introduce a concept, And when you introduce the concept, you simply call it definition. And right after that, you use the definition to somehow develop certain properties, certain identities for that concept. So here comes the next thing I'd like to do, although we took care of these. Now, I want to form this product right here, this one. Sine of Z1, cosine of Z2. Well, sine of Z1 is 1 over 2i. This. All right. Cosine of Z2 is this one divided by 2, but since I have this 2 here, that 2 cancel. Well, now I'm going to multiply this out. And in multiplication, of course, I'm going to use that exponential property of exponential function. So here is 1 over 2i. This multiplied by this one, you get the same base. You add the exponent, you'll get iz1 plus iz2. I will factor I. All right, you go through the multiplication, you get these 4 terms. Well, I am going to sort of classify based on the exponent. Here I have z1 plus z2. Here I have z1 plus z2. Let's put these together. That's what I will get. But looking at definition of sine, this is in fact sine of z1 plus z2. And this is sine of z1 minus z2. So what I found right now is this. I started with this one, twice sine of z1, sine of cosine of z2 is sine of z1 plus z2 plus sine of z1 minus z2, okay? Now, so this is valid for all complex numbers z1 and z2. No, I did not put any restriction on z1 or z2. Now, let's just switch z1, z2. Now put z2 here, z1 there, right? So this is what we get, sine of z1 plus z2 or z2 plus, it's the same. But here we will get sine of z2 minus z1. But I will factor 1 out. Now, the purpose of doing this is if I add these 2 equations now, these 2 will cancel out. On the right-hand side, I will get 2 sine of z1 plus z2. On the left, sum of these 2, okay? So this is what we get. It is familiar. It's pretty much same thing that we had in trig. Now, sine of z1, I divided by 2. Sine of z1 plus z2 is sine of z1 cosine z2 plus sine of z2 cosine z1, all right? Well, we can have the same sort of trig identity by replacing z1 by z1 plus pi over 2, and you will get the counterpart for cosine. Cosine of z1 plus z2 is cosine of z1 cosine of z2 minus sine of z1 sine of z2. Okay, so by just using this definition of sine and cosine and this little manipulative work, we discovered, we established two very important identities. Now, why do I mean important identities? Okay, let's see why that is very important. Here's why. In this identity, what happens if z1 and z2 be equal? So let's say both of them are the same, z plus z. You will get sine of 2z. On this side, you get sine of z cosine z, and again, sine z cosine z. And that is another trig identity that you had in earlier, but it is also valid in complex. So here you have sine of twice the angle is twice sine of half cosine of half, all right? Or anyway, we can have the same thing using this one. What happens if z1 and z2 are the same? You get cosine of 2z. Here you get cosine squared. Here you get sine squared. Oh, well, we can replace sine squared by 1 minus cosine squared. You get this one. Or you can express everything in terms of sine. You get this one. Right here. So if you just consider cosine of 2z equal to this, you can find cosine squared in terms of cosine of 2z and sine squared in terms of cosine of 2z, all right? We used these two in integration theory. One of the techniques of integration, when you want to integrate an even power of sine or cosine, you use these two to reduce the power of sine and cosine, all right? Okay, so the next thing to talk about is concept of derivative. Okay, well, we know that derivative of e to the iz is I e to the iz, all right? Now you use this one to find derivative of sine. Sine is right here. Derivative, and it is just derivative of these two. Denominator is a constant. And if you take derivative of this one, you will get I e to the iz, okay? Derivative of this one, negative will give you plus I e to the iz divided by 2i. I cancels, and you get cosine of z. So derivative of sine z is cosine z. and derivative of cosine z is negative sine z. So everything seems to be falling in the line with calculus, right? So we no problem there. Okay. Let's see what else we can say about these trig functions. All right. After derivatives, I'd like to tell you that no matter what z, derivative of cosine z exists, and it's negative sine z. Again here, no matter what z, always sine z has derivative, okay, and it's cosine z. Same thing with e to the z, has always derivative. These type of functions that their derivative exists all the time, or we call them entire function. So if you see this term entire function means that particular function has derivative everywhere, all right? Everywhere. Okay. In finding derivative, of course, we know that we can apply product rule, we can apply quotient rule, and all those rules also are valid. Okay. Okay. Now, something to remember from calculus. In calculus, sine of z and cosine of z, they are bounded functions. Oh, here's cosine z. Here's x-axis, and it's a y equal cosine z. It's alternative function, right? But the values of function, no matter what input, the cosine is always between 1 and -1. Okay? It's between 1 and -1. Same thing with sine. So this is in calculus. Now, the main question is this also valid in complex? In calculus, when x is a real number, sine and cosine are bounded functions. Do we have such a thing in complex? Well, for the remaining of, trig discussion, I am going to answer this question. Okay, so here's the question. In calculus, always sine x and cosine x are bounded. The functions y equals sine x or y equal cosine x are bounded. So the question is this true in complex? Is this also true in complex? As you will see, the answer is no, it's not true. But in order to prove that, you have to go through certain, oh, just remind you of two functions from calculus, which we call them cosine hyperbolic and sine hyperbolic, all right? So here is cosine hyperbolic. Cosine hyperbolic of x is just e to the x plus e to the negative x divided by 2. And nothing new, right? Nothing new, but average of e to the x and e to the negative x. And sine hyperbolic of x is this one. Well, and you see the difference between trig and hyperbolic. In trig, cosine of x, you have I here and I here. But in cosine hyperbolic, we don't have that I. Well, the derivatives, when it comes to these hyperbolic functions, derivative of cosine is, we usually say cosh. Cosine hyperbolic, say cosh, is seen and derivative of sinh, which is sine hyperbolic, is cosine hyperbolic. Just going through this, taking derivative of those two little fractions. What else do we know? Well, in trig functions, cosine squared plus sine squared is 1, the famous trig function. But here, when you form cosine hyperbolic squared minus sine hyperbolic squared, right? This square minus that square. If you go through the multiplication and simplify, you will get 1, right? You'll get 1. Oh, that's why we call it hyperbolic functions, right? It's sort of, remember the equation of a hyperbola is x squared minus y squared equal 1. Sort of, it's the simplified one. And here are pictures of cosine hyperbolic and sine hyperbolic. The graph of this is cosine hyperbolic x. Cosh is always bigger than or equal to 1. This is 1, by the way. And this is sine hyperbolic. Now, these two functions are sort of have the asymptotic behavior when x approaches infinity. All right. So when x approaches infinity, I mean, these two branches get extremely close to each other. They never touch, but gets extremely close to, and that asymptotic behavior means this. If you take limit of cosh divided by sinh, or the other way around, doesn't matter. As x approaches infinity, you will get 1, right? You will get 1. So after this little introduction of sinh and cosh and their pictures, and this main property, by the way, now I am going to go to the sine z in complex, okay, in complex. Remember, this we just developed that, right? This is true for any two complex numbers, this identity. Especially, this is true when you have x plus iy, which is sine of z. Okay, this is sine of z. So sine of x plus iy, I'm going to use this one, will be sine of x cosine of iy plus cosine of sine of iy. Okay. Now let's see what is cosine of iy and sine of iy. Remember, cosine of z is e to the iz plus e to the negative iz divided by 2. So if I replace z by iy, this is what I get. Do you have any question, Jason? Jason Vinton, do you have any question? No question. Okay, all right. Please mute yourself. Okay. That's all right. That's all right. So cosine of iy is this, which is cosine hyperbolic of y. Oh, well, we will use that one in there. How about sine of iy? Well, sine of iy becomes this one. You go ahead and multiply by and divide by I, you get this. So it is I sine hyperbolic of y. So we are going to use these two in that equation, in this equation. So sine of z, right? Sine of z, x plus iy, is sine of x cosine hyperbolic of y plus sine iy was I sine hyperbolic. So this is I. That's why we have I. Good. Good. Right. Very interesting formula. Now, the significance of this formula is we wrote sine of z as a complex number. This is its real part, and this is its imaginary part. Now we can talk about modulus of sine z. Here's modulus of sine z. Modulus of sine z squared will be its real part square plus its imaginary part square. Good. Well, I'm going to, because I know that cos square minus sin square is 1, right? We all took care of that. So I'm going to um, replace cos square by 1 plus sin square and simplify this one. Here I have sine square x plus, well, we will leave that right there. Then I will have sine square sin square cosine square sin square. If I factor sin square, sine square plus cosine square is 1. So this is what you get. Finally, this is modulus of sine z. Modulus of sine z squared is sine x squared. Well, this is bounded between -1 and 1. We know that sine x is bounded. Plus sin square y. But sine hyperbolic is not bounded. It can go from negative infinity to infinity. Okay. Let me show you the picture of sine hyperbolic. This is sine hyperbolic, the picture of sine hyperbolic. All right. The values go from negative infinity to infinity. As a result, modulus of sine z, depending on y, can become extremely huge. Right? Yeah, this is true that this is bounded. At most, this is going to be 1, but not this one. So, sine z is not bounded. Sine z is not bounded. In calculus, it was bounded, but not complex. Let me tell you what happens. In calculus, if they give you this equation, find the x so that sine of x is 5. You would say, are you crazy? Sine of x is always between -1 and 1. Cannot be 5. That was in calculus. But in complex, things are different. In complex, can we find a z such that sine of z be 5? Okay, let's do this one. Let's do this one. It's a very interesting one. Okay. You remember definition of sine z. This is sine z. E to the iz minus e to the negative iz divided by 2I. We want this to be 5. You multiply out. You multiply both sides by 2I. This is what you get. Then you multiply by e to the iz. Here you get e to the 2iz. Here, -1. On the right side, 10I will be multiplied by e to the iz. Bring everything to one side. You get this equation. This is a quadratic equation. If you call e to the iz a, actually you have a squared here minus 10I a minus 1 equals 0. this is actually giving us a quadratic equation. Can we solve this quadratic equation? Sure. Let's go ahead and use quadratic formula. By the way, quadratic formula works here as well. So here is, negative b plus minus b squared minus 4ac divided by 2a, or a is. So using quadratic formula, you get this one. And here is negative 96. And negative 96 actually is I square root of 96. And 96 is there, so 2 comes out. And you simplify. This is what we get. So A is 5i plus minus 2 is square root of 6. Okay? But regardless of plus or minus, this is something. This parenthesis is something positive, because you see here you have 10, but here you have 96, right? Which is smaller than 10. So this is positive. Can I write this in polar format? Yeah, it's going to be here. It's positive. I'm going to work with 5 plus, so the modulus of this one is this number. The argument is pi over 2 because it's right here along this y-axis. It's completely, imaginary. We don't have a real part. All of it is just a number times I. So if you write it in polar format, and remember A was e to the ic. So e to the ic will be this, e to the pi over 2i. However, we then we can take the log of both sides. I will talk about log momentarily. So e to the ic will be this. And whenever in complex analysis, whenever you have two exponential forms equal, you cannot say z1 equals z2. That's just one solution. In general, you got to say z1 is z2 plus 2k pi I. That is what we are going to do here. So iz is this. And you divide by I. That z is going to be right here. Okay, I worked with plus, but if you work with minus, you get minus out. So this is a complex number. Our goal was to find all values of z for which sine of z is 5. So we don't have just one solution. We have infinitely many solutions depending on k. K can be 0. I mean, k is an integer. So what is the message here? The main message is, look, in real analysis, in calculus that you took, sine x, cosine x, they were bounded functions between -1 and 1. But when it comes to complex, they are unbounded. Unbounded. In calculus, sine of x equal 5 doesn't make sense. But in complex, it does. Not only sine z equal 5 makes sense. Put any number here, any number. That makes sense. Okay? That's the message. The last thing I wanted to say about trig functions. Remember, both sine x and cosine x are in trig functions are unbounded in complex analysis. Okay, good. Any comment, any question? That pretty much takes care of 13.6. And when it comes to, yeah, I just finished whatever I wanted to talk about, although we can still say a lot about trig functions in complex, but based on your text, which is so brief, it's written for engineers, that seems to be enough. Unless you have any question, then I will be more than happy to answer those questions. The next thing to talk about is 13.7. Okay. Now, of course, you can go ahead and do problems of 13.6. But when it comes to 13.7, all right, let me tell you what happens in 13.7. I might not completely cover it today, but I will do my best. I'm going to talk about just a review of exponential function from calculus. This is exponential function e to the x. Right? Always positive, right? Always positive. It is defined for every real number, regardless of negative or positive. It's e to the x. It's defined everywhere. So that is a symbol. Domain of e to the x is everything. How about its range? How about its values? Well, its values, as you see, the values means what portion of the y-axis this curve is going to cover. First of all, e to the x can never be 0 and can never be negative. So it's always positive. Here is the notation, meaning that its domain is everything. But when it comes to output, it's always positive between 0 and infinity. Well, one more thing. This function is strictly increasing. Is 1 to 1, strictly increasing. Okay? Maybe I should write here. This is 1 to 1, strictly increasing function. As a result, it has what we call an inverse. Inverse of this function, e to the x, we call it log x. This is the log. Okay, this is e to the x. This is log x. The picture of a function and its inverse is going to be a mirror image with respect to y equal x. So this is log x, y equal log x. I'll look at the behavior of log x. E to the x goes in this direction. Log x goes the other way around. So here is log x. The domain is 0 to infinity, right? You cannot have log of 0. You cannot have log of a negative number in calculus. Okay. In calculus, such a thing doesn't make sense because domain of this log is here. The input has got to be here, and the output, of course, goes every covers a real number system. Okay. Well, after this little review, of course, we call this in calculus one is inverse of the other, and the being inverse of each other, we know that if we compose them, we will get back to the original. For example, log of e to the x is x, right? And e to the log x is also x. Compose them. Whatever log does, e to the x undoes it. Whatever e to the x does, log x undoes it. So when you combine them, when you compose them, you will get the original x out. Okay, having said that, now let's go to the complex e to the z. Here is e to the z, we already knew. And when you take modulus of e to the z, it's e to the x, never 0. So modulus is always. So e to the z can never be 0. That's the message here. But if you have z, if you have here a complex number, based on this one, you can find the result. We can find the result of e to the z. What I want to do is the other way around. If you have is a complex number, which is not 0, because can we find another complex number so that e to the a plus bi become this z? So here's the question. Given z, for example here, 2 plus the square root of 2i, can we find a complex number a plus bi so that this be equal the exponential can be equal to 2 plus I, square root of 2i? That's the question, all right? If there is such a thing, we want to find this a and b, right? We want to find this a and b. Okay, let's work on this. Suppose such a thing is possible, and we take modulus of both sides. Modulus of the left side is e to the a. Modulus of the right side is this. Now, these are not real numbers, all right? There's no I involved in here. You take natural log of both sides. A will be natural log of modulus of c. So we found A. We found A. If such a thing is possible, that A was found. Next, after finding A, so we know that e to the a is going to be natural log of c. So here is e to the a plus ib. Here is the given number, all right, given number, written in exponential format or polar format. So from this equation, I know that e to the a is equal this. So let's divide by that. Then e to the ib will be e to the I theta. And remember, as soon as we have two exponential equal, we cannot simply say ib equals I theta. No, no, no. There might be a 2k pi I things, and here is b. B will be theta plus 2k pi. Oh, we found b as well. We found b. So here is a plus b. A is natural log of modulus of z, and b is this. So e to the this will be z. Okay, this is what we call logarithm of z. So in complex analysis, when you have a complex number, log of z will be this. And this is the argument of z. Theta, remember, theta was one of the arguments. And if we use the principal argument of z that usually we do, it's called principal branch. So if you use principal argument of z, remember, principal argument has to be between negative pi and pi. Oh, we call this one principal branch of log z. So log of z has a lot of answers depending on this key, k. For when we choose the principal argument, then it will be a one single valued function, all right, single valued function. All right, so that is definition of logarithm in complex analysis. Let me give you an example here. So just repeating this for the sake of remembering what we are doing. So the question is, giving a complex number, can we find a complex number w so that e to the w be z? If we find such a thing, that is called log of z. And log of z, we just noticed that is right here. Here's an example. I want to find log of 1 plus I. And this capital L, uppercase L, means the principal branch, all right? The principal branch. So you go ahead and plot the number. This is 1 plus I. Modulus, here is 1, here is 1. So modulus z is the square root of 2. So logarithm, and an argument is pi over 4, by the way, principal argument. So based on this formula, here is natural log of the square root of 2 plus pi over I. Okay? This is a very good example of finding logarithm. Any comment? Any question? Okay. I don't know, maybe another example will be appropriate here. Let's do another example. I want to find, please note here, I am not using capital L. I'm just using ln. And as soon as you see this one, that means find all values of this. But all values, definitely, you got to plot the point. Here is the point, the square root of 3 right here, and -1. So the principal argument is negative pi over 6. And the modulus is 2. So in using this exponential format, this is in fact 2 e to the negative pi over 6 I, this being the principal argument. As a result, the log of this guy is log of 2. This is the principal argument, negative pi over 6 I, plus 2k pi I. Okay? This is all values of this. If you stop right here, if you do this, this is going to be the principal value of logarithm. But if you, and that we will denote it by capital L. But if you don't have capital L, that means find all values, and all values are. There are infinitely many results when you take logarithm of something. Infinitely many. One of them is the principal argument. Okay, so here, this is the principal one. Well, theta is going to be the principal argument. Okay. Any comment? Any question? Well, I just introduced the function logarithm. That's good enough. If you want to read in advance, please do so. I'm going to continue this one on Thursday. I just gave you the definition of logarithm in 13.7 here. But the properties and the derivative and some other stuff is remaining. So I will try to cover those on Thursday together with starting a new chapter, chapter 14. Okay? Any comment? Any question? No question? I don't see any question. Well, if there is no question, then I will see you on Thursday. Have a good day, everybody. Thank you, Ernesto, Matthew, Jason, Corey. Thank you. Thank you. Have a good day, everybody. Thank you, Dell. Thank you, Fox.